Hello everyone, I'm Jiayi from Fudan University. It's my great pleasure to take part in FG 2023, and I'm very glad to introduce our new work to all of you. Many approaches have been developed to extract and aggregate local features for better facial representations. Regional attention networks propose to crop the initial input sample into several copies and utilize the attention mechanism to reweight and aggregate their features. Gated attention convolution networks propose to encode the input sample first, then extract local features according to the location of the landmarks. Then utilize the attention mechanism to reweight and the features of the landmarks. However, how to learn an optimal global representation is not well explored. In this work, we propose to utilize cascaded deletion convolution layers to achieve global receptive field and utilize class-sensitive metric learning to extract effective global features. The first problem we are going to face is the so-called grading problem. That is, for the neuron in red, we enclose the pixels that could be seen by it with a red box. There are many pixels in white that cannot be seen. One proves that 3 cascaded deletion convolutions, which meet the inequivalent in equation 1, can avoid the grading problem. However, since we want to achieve a global receptive field, we have to expand this to more than 3 deletion convolutions. First, we call the box which encloses all the pixels which could be seen by the neuron as its receptive field. So the radius of the receptive field is the maximum infinite norm between the pixels and the neurons. The receptive field of n deletion convolution layers with deletion rates Ri, I from 1 to n, which satisfy Rg plus 1, is not smaller than Rj. We have the radius equals the summation of the deletion rates. This is an example in which R1 equals to 1, R2 equals to 2, so that the radius of the receptive field in brown, of the neuron in brown, is 3, and the diameter of the receptive field is 2 multiples of the radius plus 1, which is 7. In this page, the left figure has no grading problem, and the right one has grading problem. Consider the neuron in red can see the output of the neurons in orange. Grading problem appears because the receptive field of the neurons in orange, their receptive field are not adjacent to each other and not adjacent to the neuron in red. In fact, we can have this conclusion. If n layers have no grading problem, when the additional deletion convolution has a deletion rate which is smaller than the diameter of the former deletion convolutions, all these deletion convolution layers have no grading problem. Based on the aforementioned conclusions, we built a mobile deletion module, or MDM. Denote L as the size of the feature map. The number of deletion calculation layers is calculated by the Argmax equation, where Ri is the deletion rate of the ith deletion convolution layer. In fact, we can easily prove that this setting meets the aforementioned inequivalent. This is our framework. First, we adopt an random spatial transformation to the samples to build couples of the initial samples. Then we use the ResNet backbone with MDMs to extract the features of the samples and their copies. We minimize the distances between original samples and their corresponding copies, and the distances between the samples with the same expression. We maximize the distances of the samples from different classes. This part is called class-sensitive metric learning module. Class-sensitive metric learning has 2 parts of loss functions. The first part is called alignment loss. Denote L and hat L as the features of the initial sample and its copy, and P is a classification layer. We minimize the mean absolute error of the features in pair, and minimize the KL divergence of the output of the classification head. The second part is called soft nearest neighbor loss, which is for minimizing the intra-class distance and maximizing the inter-class distance. We validate the proposed method on 3 different datasets, which include RefDB, FER+, and SFEW. Experiments show that the proposed method achieves the state-of-the-art performance on all these 3 datasets. The left table shows the performance on challenging datasets. The result shows that the proposed JCNet has less performance gap on the full test set and the collected subset with occlusions or heavy pulses, which shows that the proposed method is less vulnerable compared to regional attention networks. The right top table shows that both MDM and the class-sensitive metric learning can boost the baseline model a lot. And the right bottom table shows that the MDMs on different stages can boost the baseline model similarly. The figure shows the contributions of the pixels to the centroid pixel by gradient. Figure A to C show the receptive field of self-attention, normal convolutions, and deletion convolutions, respectively. Although self-attention achieves global receptive field theoretically, since the tokens with higher similarity are considered more important, it sometimes focuses on only the neighboring pixels. Normal convolution layers cannot achieve global receptive field, while the cascaded deletion convolution layers achieves that. The right top table shows that normal convolutions can only slightly boost the baseline model, while the deletion convolutions and self-attention dramatically increased the baseline, which shows that the receptive field really matters. Compared to self-attention, the deletion convolutions shows better performance, which indicates that if the effective receptive field is more important than the theoretical global receptive field. The right bottom table shows that we make the MDMs k times deeper. Result shows that deeper MDMs can further boost the baseline model from 90.1 accuracy percent to 90.4 percent of accuracy. This is our work. Thank you for watching.